Hello and welcome to a virtual Venny video. It's nice to see you guys. Obviously I'm not here today. I'm taking a group of students down to Houston this week, and so I'll be missing class with you guys today, but I should be back on Friday, so I guess that's the good news. So today we've got an action-packed agenda, which I'll go over shortly, but first I'd like to talk about the warm-up question. Last block when we were together, we were learning about basically this idea that wires that create current generate a magnetic field that wrap around that wire. And so today's warm-up question is asking for you to determine the direction of the magnetic field around this wire. Well, if we try to do that, basically what's going to happen here is this wire, the current is going like up relative to the piece of paper, and we need to figure out the direction of the magnetic field. And so if I try to do that, basically I would want to use the first right hand rule, where my thumb is in the direction of the current and my finger pads point in the direction of the magnetic field. So on the right side of this wire, if I put my thumb up where the arrow is pointing, my finger pads would be pointing into the paper. And the symbol for into the paper would be a circle with an X on it. So I would have a bunch of circles with X's around it. On the left side of the arrow, so over on this side over here, if I put my thumb in the direction of the current and I move my hand to be where I want to figure out the direction of the magnetic field, I would see that my finger pads are pointing directly up at my face. And so the magnetic field is actually coming out of the page, and the way to represent that is a circle with a dot. So you have to use your imagination here a little bit because we are thinking 3D right now, but basically this magnetic field is literally wrapping around this wire, and I'm not a real good artist, but this is supposed to represent it wrapping around the wire, dotted lines kind of going behind the wire. So this whole wire is creating this magnetic field, and that's really what last block was kind of about, was this idea that current carrying wires generate magnetic fields. Okay, so let's talk about what we're doing today. We're going to kick class off with some notes. So if you want to grab your notebooks, I'm going to go through them with you actually. And then after the notes, we'll have you pause the video, and I've got some practice problems for you guys to try. So basically it's a worksheet that you'll want to turn in when you're done with it. And if you don't understand a question, you're confused about something, don't stress about it. Just circle it and come to class on Friday ready to ask a question about it, because I hopefully will be back and be able to answer those types of questions. After the practice problems, I'm going to basically have another physics teacher walk you through how a electric motor works. So for you guys, it's going to be a video, and if you have questions about questions about the video afterwards, I'd be happy to answer them once I'm back on Friday. Then we're going to do a lab where I'm going to have you guys actually try to build a motor. And once you're done with that lab, you're going to have to just turn in a half sheet of paper, basically that has you draw a diagram of the motor and explain how it works. Finally, to wrap the block up, we do have an AOR scheduled for today, so get excited for that. Okay, so hopefully you have your notebooks out, and we'll go through the notes together and kind of learn what's new today. So these notes are called 8.2 magnetic force, and basically what we're doing today is we are actually learning about a new force. So it's pretty exciting. We are learning about the magnetic force. This force is another force that acts over a distance, so you don't need to be in direct contact with a magnet. And if any of you have ever played with magnets before, I think you all know that if you move them close to one another, they're going to interact with each other. Either they're going to attract or repel each other. And that push or pull that you're feeling actually is a force, and it's the magnetic force. So pretty cool. So we're going to learn about that today. And then we're going to learn about, this is actually supposed to say the third right-hand rule, and how that right-hand rule can be determining the direction of the magnetic force. And I'm going to give you some equations. So we're going to put some math behind this so we actually can calculate how many newtons of force this magnetic force is generating. Okay? So we learned last block that currents create magnetic fields. Right? So a current-carrying wire will make this magnetic field surrounding it. We're able to determine the direction of this magnetic field using the first right-hand rule, where your thumb points in the direction of the current and your finger pads point in the direction that the magnetic field would point. The magnetic field that's created by that wire will actually supply a force to a charged particle or another magnet or wire that's generating a magnetic field. And we have to think back to our unit on statics when we talk about charged particles. If you think back to the parts of an atom, protons and electrons are actually charged particles. So if you send a proton or an electron through a magnetic field, it's going to experience a force. The same is true if you put a wire in a magnetic field, it will experience a force as well. And that's really what we're trying to learn today, is this idea that wires and charged particles will experience forces once they're placed in a magnetic field. So before we get into actually the equations, we know forces are vectors, right? At least I hope we know that by this point in the year. And so that means they have a magnitude, which is a number value, and a direction attached to them. Believe it or not, the direction is probably the harder of the two things to learn in this unit, because we have to use these right-hand rules to figure out what direction the force actually points. And the reason why it's challenging is because these magnetic forces act in 3 dimensions: the x-axis, the y-axis, and then the third dimension, which is called the z-axis. And the reason why this occurs is because the force, the current, and the magnetic field are all perpendicular to each other. So you got all sorts of different directions going on here. I know it's just a little strange compared to some of the other topics we've explored in this class, and we've had just directions where it's either left, right, up, down, or whatever. Well, now we're adding into the page and out of the page, and that makes it a little bit more tricky. So we're first going to learn how do we calculate the direction of the force, and then after that we'll learn how to calculate the magnitude of the force. So here it is in all its glory, the third right-hand rule. Now I encourage you all to kind of play around with this as I'm doing it as well. It's really hard for me to do it because I think everything's going to be flipped on the screen, so I'm not going to really put my right hand up too much. I might just draw pictures for you, and then once I get back to class on Friday we can start to do this together. But these are the rules for determining the direction of the magnetic force. You'll see some similarities to the first right-hand rule, but also then some differences. So the first thing I'd like to talk about is that your fingers, or I should say your fingertips, point in the direction of the magnetic field. So if you take a look at this hand up here in the top right corner, the symbol for the magnetic field is the letter B. The B field extends from this person's fingertips, not the pads, but the tips themselves. The thumb points in the direction of the current or a moving charged particle, and the palm of the person's hand points in the direction of the force. So whenever you use this third right-hand rule, your hand's always going to be looking kind of like this, where you're almost like you're going to shake someone's hand, where your thumb is coming directly out and your fingertips point straight up. You'll see people do this differently. Like I'm going to show you some videos today of different physics teachers, and they'll do things like they'll make like a little gun-looking thing. You'll see people curl their hands like this. There's all these different ways you can really go about using the right-hand rules, and so the way you learn it in this class, if you take physics later on in life, will probably be different with your next instructor that you get. The way I show it to you guys, in my opinion, is the easiest and least likely for you to have mistakes. So that's why I kind of do it this way. So I encourage you actually not to curl your fingers at all, but instead keep your hand in this shape, and your thumb points in the direction of the current, your fingertips point in the direction of the magnetic field, and the palm of your hand points in the direction of the magnetic force. You'll notice there's an important piece to this, and that's that if the charge is negative, so let's say it's an electron, if it's an electron, you have to flip the direction of the force. So let's say you calculate the force to be up, but if the problem says it's an electron, the force is actually down. If you were to calculate that the direction of the force was right, and it turned out to be an electron, the force is actually to the left. Okay, so it's always going to flip. And I'll show you examples of this in just a second. In the next slide, this is a video of a teacher who basically does a demonstration where they have a wire, this kind of like copper rod is basically acting as a wire, and it's put inside of a big magnet. He'll explain the experiment to you, and it's nothing super exciting that happens really as this experiment occurs, but it actually is a revolutionary thing that was discovered once we figured out that current carrying wires actually interact with magnets. It's actually a really cool thing, and we'll explain why as we move on later through the block. So take a look at this video. Realize this guy does the third right hand rule differently than I do, so just I wouldn't listen to that so much, but just kind of watch the experiment, and we'll get back together shortly.
So I have here a large magnet, South Pole, North Pole, so the field is pointing up. And then I have a big, copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red, through the copper tube, and then up through ground, and then back home. So we'll have electricity flowing this way, magnetic field pointing up. We expect a force inward. And sure enough, we get an inward force. Now, if I reverse the direction of the current, we expect an outward force. I'll get this guy out of the way. And there you see it, floating there. Because now that I've reversed the direction of the current, current is flowing this way, magnetic field is pointing up, we expect an outward force. And that's what you see. Right hand rule, simplified.